Only nodes that are closer to the destination than the source are included in the potential forwarder set. Each packet carries a bitmap, marking packets that have been received by the sending node or nodes with higher priorities. A forwarder transmits a packet only if no forwarder with higher priority has explicitly acknowledged receipt of it. XOR has good routing performance. It is unlikely that a forwarder will receive the entire batch correctly, so the nodes that have stored fragments of the batch will need to schedule their transmissions. To that end, each forwarder uses a forwarding timer that XOR has set to 5 packet durations times the number of higher priority nodes in the forwarder list, and which is a prediction of the time at which the node should start forwarding packets from its packet buffer. After each schedule cycle, the batch maps need to be updated by means of negative acknowledgements, and when the destination has received 90% of the batch, the rest of it is sent using traditional routing, because the overhead would be forbidding otherwise. Due to the centralized coordination and scheduling that is needed between forwarders and the destination, XOR incurs high overhead when the batch of packets to transmit is small, as in bursty and short-lived flows, or the number of candidate forwarders is large. The SOAR protocol has been proposed as an improvement to XOR in order to support multiple flows. In SOAR, the candidate forwarders are constrained to be on or near the shortest path from source to destination. The cost metric is again ETX. A significant difference between XOR and SOAR is that SOAR performs the routing decision process on a per packet basis rather than on a batch. Finally, in SOAR the forwarder list is limited to 5 relays. Overall, SOAR incurs slightly less overhead than XOR and restricts flows as close to the shortest path from source to destination as possible. It is considered crucial to avoid diverging paths, and select forwarders that can hear each other, because overhearing is the only means to avoid duplicate transmissions. To make the protocol reliable to ACK losses, selective ACKs are used. Each ACK packet contains the starting sequence number of out-of-order ACKs and a bitmap of out-of-order ACKs. In addition, SOAR uses a scheme of piggybacked acknowledgement and ACKs compression to reduce the overhead of acknowledgements. When a node does not have much data to send, it should also send standalone ACKs to provide timely channel feedback. However, the increase in throughput that is observed when SOAR is in use is partly due to its opportunistic scheme and partly due to its complex acknowledgement scheme, therefore making it unclear at what extent this protocol contributes to opportunistic routing. In Roamer, a credit mechanism is used to build a forwarding mesh topology on the fly centered on minimum cost paths. It aims to avoid the cost of retransmissions over persistently poor routes. Each packet is assigned a number of credits equal to the amount needed to reach the destination along the minimum cost path plus some extra slack, allowing the packet to deviate slightly from this, shortest, path. Before forwarding a packet, the transmitting node calculates the remaining credit that the packet would have if forwarded over a link and compares it to a threshold value. This scheme enables multiple forwarders to emerge near the source to ensuring route diversity and packet progress in view of lossy links. At the same time, the scheme secures converge near the destination and remains close to the minimum cost path. Greedy probabilistic forwarding is used to deliver the data packet along the instantaneously highest rate link with probability 1 and along other high-rated downstream links with a high probability value. Thus, it favors high-quality links over low-quality ones by selecting higher random forwarding probability. However, it does not account for resource conservation and catering to multiple flows. The parametric probabilistic sensor network routing scheme proposes 2 protocols that forward a single packet with varying retransmission probability through a network of sensor nodes, focusing on simplicity and robustness to errors in distance estimation. The destination attractor assigns a higher retransmission probability to the packet, as it moves closer to the destination, and reduces it, as the packet moves away from the destination. Distance check is performed by comparing the distance of the source node in hops from the destination to the distance of the node currently holding the packet. The primary concern of this approach is to deliver as many copies of a single packet to the destination sensor as possible, without accounting for resource usage or delays. Directed transmission improves probabilistic routing's performance by assigning an exponentially higher forwarding probability to nodes that are on the shortest path from the source to the destination and decreasing it as the packet strays from the shortest path. This leads to lower resource consumption than the destination attractor and can be tuned to resemble shortest path routing, when the misinformation is low enough. Both protocols are compared to shortest path routing as an ideal case.